Hi Year 11, this is our last video for the topic of probability. In this video we'll look at conditional probability. So far we've covered theoretical probability and experimental probability, set theory, Venn diagrams, the laws of probability, and independent events. Conditional probability involves calculating a probability given another event has occurred. And this is the formula that we use, and it's given for you on your reference sheet. This is how we write it. The probability of A given B. And it's equal to the probability of A intersection B divided by the probability of B. Here's an example. A group of 25 students either studies chemistry or biology or neither. It is found that 15 study chemistry, 14 study biology, and 6 study only biology. Now, this question is subtly different than the ones we did in the last video. We're going to do it a different way. We're not just going to add these numbers up and find out how much bigger the total is than the number of students we have. Have a look at this here. 6 study only biology. We're going to start there. So that's this part here. Then we're told that 14 study biology, that's this whole circle. So 14 take away 6 is 8. And 15 study chemistry, that's this circle here. We've already accounted for 8 of them. 15 take away 8 is 7. Now we're going to add them up. 7 and 8 is 15 and 6 is 21. We have 25 students, so 4 study neither chemistry nor biology. Now here's the question. Find the probability that a student chosen at random studies chemistry given that they study biology. Now rather than use the formula, we're actually going to do this question by restricting the sample space. So the students who study biology are here. So given that this student studies biology, what's the probability that they study chemistry? Can you see it would be 8 out of 14? And that's actually the answer. Now we can use the formula. We will get the right answer. It's just more work. Here's the formula. Probability that the student studies chemistry given they study biology is the probability they study chemistry and biology divided by the probability they study biology. So this probability here is going to be 8 out of 25, and this probability is 14 out of 25. And you can see that those 25s cancel out and we end up with the same answer, 8 out of 14. So in that previous example, it was easier not to use the formula and just to use the context of the situation. But if you have no context, like this question, you have no choice but to use the formula. Find the probability of A intersection B if the probability of A given B is 5/12 and the probability of B is 3/5. So here's our formula. This is what we want, and we know both of these. So substituting in and then multiplying both sides by 3/5, we get our answer, which is 1/4. Now sometimes it might seem as if you don't have enough information. Have a look at this example. Given the probability of A union B is 0.8, and the probability of A intersection not B is 0.45. Find the probability of A given not B. So we'll start with the formula. The probability of A given not B is equal to the probability of A intersection not B divided by the probability of not B. Now we do know the numerator, it's 0.45, but we don't know the probability of B or its complement. So let's go to a Venn diagram. Now there I have highlighted A union B, and we know the probability of A union B is 0.8. This region here, this is everything in A that's not in B. It's that cookie region here. Now if we know that A union B is 0.8, and that's this yellow region, outside of that must be 0.2. And from this we can work out the probability of not B. It's everything outside this circle. So it's going to be 0.2 plus 0.45, which is 0.65. And just using the calculator, we get 9/13. Now let's return to tree diagrams and have a look at conditional probabilities in tree diagrams. Do you remember this example? Sam chooses 2 counters from a bag containing 3 blue and 4 white counters. She does not replace the first counter after it's drawn. So remember when we drew the tree diagram up, we worked out the probabilities that she draws a blue counter and a white counter. And then when we were looking at the second event, the second counter, we had to consider what had happened beforehand. Well, these are conditional probabilities. They've actually been affected by a previous event. So this probability here is the probability that she draws a blue given she has already drawn a blue. This one here is the probability that she draws a white given she's already drawn a blue. So what's the probability that she draws a blue given she's already drawn a white? Well, that would be 3/6. Now it is different to the probability that she draws a white and then a blue, because in this case we would multiply these probabilities together. So we'd do 4/7 multiplied by 3/6, which is 2/7. And this is what you're given on the reference sheet. We have the rule for independent events, the addition law, and then we have the conditional probability formula. Okay, one last thing to finish off. If A and B are independent events, then we can simplify the conditional probability formula. So here's the formula. The probability of A given B is equal to the probability of A intersection B divided by the probability of B. Now we know that if A and B are independent, then this is the same as probability of A multiplied by the probability of B. And have a look at this. These probabilities cancel. So with independent events, the probability of A given B has occurred is equal to the probability of A. And this actually makes sense because there is no relationship or dependence between these events. The probability of A is not affected by whether B has occurred or not. Last example. Suppose the probability of A is equal to 0.45. The probability of B given A is 0.25. And the probability of B given not A is 0.2, find the probability of B. So we'll start by using the formula for this. It's equal to the probability of B intersection A divided by the probability of A. And we know the probability of A, it's 0.45. So bring this up and over the other side, we end up with the probability of B intersection A is 0.1125. Now let's do the same thing with this. So it's going to be equal to the probability of B intersection not A divided by the probability of not A, and that's equal to 0.2. Well, if we know the probability of A is 0.45, the probability of the complement of A must be 0.55. And we're going to do the same thing. Bring this up and over the other side, and we get the probability of B intersection not A is equal to 0.11. Now what does that mean? Well, let's go to our Venn diagram. The probability of B intersection A, so that's in the middle here, is 0.1125. And this, the probability of B intersection not A, so remember that's everything in B that's not in A, so that's over here, is 0.11. And we can figure out the probability of B, can't we? We just need to add these two together. So the probability of B is going to be 0.2225. And finally, are A and B independent events? Justify your answer. Now we could work out the probability of A intersection B and see if that's equal to the probability of A multiplied by the probability of B. But there is an easier way. If A and B are independent, then the probability of B given A must be just equal to the probability of A. And we already know this. This is 0.25 and this is 0.45. So A and B are not independent. Okay, that's it for the topic. Our next probability topic is discrete random variables.